Well, hello and welcome, everybody. Hey, got a pair of really similar questions here. I think it's kind of fun. Here they are. Here's what we'll do. I'll run you through the details, then give you a chance to try them on your own, and then I'll run through how I did them. And I'd really love to hear if you got the same answer, if you've came up with a different way of doing it, and well, anything else you'd like to share with me. I really love reading your comments and responding to them, so I'd love to hear from you in this one as well. All right, so here's what we got. On the first one on the left, we've got two circles. The small circle has a radius of 2. The larger circle has a radius of 4. And BD and BE are both tangent to circle with the center of A. We call that circle A. And those lines and the edges of the circle create these little regions right here that are shaded red. And our job is to figure out what's the area of the shaded region. All right. And problem 2, really similar, but here the two circles are the same size. The radius of circle J and the radius of circle K, they're the same, but we still have JN and JM that are tangent to this circle over here, creating this area. But now we don't know how big the circles are, but we do know that the area of the shaded region is 8 times the square root of 3 minus 4 pi, and our job is to figure out how far apart are the circle's centers. So pretty cool problems right there. Why don't you go ahead and pause the video, give it a shot. Let me know what you think. All right, we're going to get into it right now. All right. So our first one, here's what we've got. We've got a circle, radius of 2, and another circle, radius of 4. They're connected. The two circles touch just like that. So we'll call those points A, B, and C. The center of the large circle A, center of the small circle B. And BD is tangent to circle A, and BE is also tangent to circle A, and our job is to figure out what is the area of this shaded region that is red. All right, well, let's dive into this one. I think the best way to start is, of course, with the stuff you're given and what those things mean. So we've got radius of 2 and a radius of 4, and we know that these two segments, BD and BE, are both tangent. So starting with from there, what's really easy is we know that those two angles, BDA and BEA, are both right angles because, well, tangent line is perpendicular to the radius of the circle at the point of tangency. So we know that those two are perpendicular. All right. Now, we have to find this shaded region. So I think perhaps one of the trickiest things is actually to figure out what is that shaded region made of. Like, that's a composite area. How could we maybe break it apart so we can actually figure out some shapes that we could tackle? Well, let's see here. Let's see if we can kind of clean this up. I'm going to take the two circles away, and when I look at it like this, well, look what we've got. We've got a triangle on the top and a triangle on the bottom and two sectors. So I've got this triangle right here. It's a right triangle, right? And that's going to be the outside of the whole thing if I have those two triangles. Now, those two triangles, let's see if they're actually the same or not. It seems like they should be, but let's go ahead and double check. So I know that those two sides are both 4 because those are the radius of the big circle. And it was given that the radius of the small circle was 2 and the bigger one was 4. So that would be a distance of 6, which gives us this side over here using the Pythagorean theorem, right? Square root of 6 squared minus 4 squared would be that distance. Same one down here. So, yep. We have side angle side right here. We have a 90-degree angle. So, yeah, these two are exactly the same. A couple different ways we could show that, but they are the same. So, if we start off with those two triangles, which actually form a kite, and we take away this sector, and then we take away the other sector over here that we'll shade in green, what we're left with is the red area right there, this red region. All right, well, let's see if we can tackle those. Let's go ahead and make our little picture formula up here in the top right corner. We've got our two triangles, the kite, minus our two sectors. So let's see if we can start off by finding the area of those two triangles. So we'll start with this one, ABD. We'll move it on the side so we can see it a little better. We know that the base right here, AD, is 4, and we know the hypotenuse is 6. We could use the Pythagorean theorem and find out that the height from B to D is 2 root 5. All right, so 2 root 5. Now the area of a triangle, well, is 1/2 base times height, but we've got 2 of them. So we're going to multiply by 2, ending up with the area of the kite is just base times height. All right, let's plug in the things we know. That we know the base is 4. The perpendicular height to that is 2 root 5. So multiplying that together, we get that the area of both triangles put together is 8 times the square root of 5. So we'll tuck that away for future reference. Now let's tackle those sectors. First one right here. You see it? Well, we need the sector angle. We're going to use the triangle to help us figure out the sector angle, right? We know that both of those sides are 4. We know that we know that this right here is actually 6. So we can use, well, just right angle trigonometry, because this is a right angle up here. So cosine of this angle would be 4/6. So the angle would be the arc cosine of 4/6. All right, now the thing is we have 2 of them, so we're just going to go ahead and double that and figure out what our angle is. So we've got 2 times arc cosine of 4/6. That's the angle we need. And plugging that into the calculator and rounding to 3 significant figures, which is a nice way to start. 96.4 degrees is our central angle. So we know that central angle is 96.4. We know that the radius is 4. The area for, well, the formula for the sector area, and the area of a sector is the angle divided by 360. That's the portion of the entire circle we have, times the area of the circle, pi r squared. So 96.4 divided by 360, plugging all that in, we get 4.28 rounded to 3 significant figures. But I thought it was kind of interesting that that 4 was repeating. I didn't know if that was going to be useful or not, but maybe. So we've got 4.28 pi is the area of the first sector. Now, let's see here. Let's go ahead and plug in the values and see if we can figure out the other one over here in green. Now, let's call that angle alpha. And what we know is that this is a quadrilateral, ABED, right? And we know that this angle up here with the vertex of D and this one right here with the vertex of E, those are both 90 degrees. So all the angles of a quadrilateral add up to 360. We know this one, so this angle over here and this one here must add up to 180 because those other 2 are 180. All right, so 180 minus 2 theta, and we end up finding out that the angle over here is 83.6 using the same formula, right? Theta divided by 360 times pi r squared. Plugging in our numbers, let's plug it into a calculator, 0.929 rounded to 3 significant figures times pi, which seems kind of silly, but that's going to come into play and give us a clue for our second question in a minute. So I didn't multiply by pi for that very reason. So here's what our parts are. We've got that the 2 triangles are 8 root 5. We've got that this first sector is 4.28 pi, and the smaller sector is 0.929 times pi. All right, well, let's see. If we plug all those things in, right, combine like terms, we find out that unrounded, we get 8 root 5 minus 5.21 pi. If we put that into a calculator, we get approximately 1.521, whatever the units are, squared. So that would be our area. Pretty cool, pretty cool. So we know that for the first one right here, the area of the region shaded red is 8 root 5 minus 5.21 pi. Now in the second one, and this is where it's pretty cool, we're told that the area is 8 root 3 minus 4 pi. And those 2 things, as you can see, oh man, do you see how the triangle has a square root in it? Oh, and the area of the sectors combined, they still have a pi. Now this second question, it's a lot cleaner, like this 5.21, kind of ugly, but yeah, there we go. So we're going to see that those 2 things are related. So the triangle comes from the square root, right? The square root, I should say, comes from the triangle, and the pi comes from the sectors. And so in our new problem, on our second problem, we're going to set it up just like that. Let's get into that, shall we? Actually, if you haven't tried the second one yet and you'd like to, or maybe you got stuck, maybe this is enough clue to get you started. So go ahead and pause the video, and we'll dive into it right now. All right, part 2, here we go. So we've got this diagram right here. We've got the 2 circles. They're equal. They're congruent, right? They have the same radius. And we have to find how far apart, what is the distance between A and B. I went ahead and changed the letters on this just because, well, I don't know. I like A, B, D, and E more than the J's, the K's, the M's, and the N's. They're kind of hard to tell apart when you're speaking. But anyway, let's go ahead and dive into this one. So we know that the triangles they produce the square root, and we know that the pi comes from, well, the sectors. So we're going to use that as a little bit of a clue. So we're going to see if we can go ahead and break this down and see if we can write an expression for each of those. So let's start off with the triangles. So if I put ABD right here, it's a right triangle because AD is tangent to circle B over here, right? And I know that I have two of those triangles, right? So instead of 1/2 base times height, I'm going to have two of them, and I have BD times AD. Right? It's a right triangle. I don't know what they are, but that would be my area. So cleaning up the 1/2 times 2, I get BD times AD. Now, here's the thing. BD is the radius. So what I actually have for the area of both of the triangles, or the kite, is pretty rad. See what I did there? Sorry. It's the radius times AD. All right. So we have an expression now for our 8√3 that we're going to maybe be able to figure out here in a minute. Let's go ahead and see if we can write something for the two sectors. Now, let's go ahead and start off last time like we did with our angle. We know that this angle would be the cosine of this angle would be the radius divided by the hypotenuse, AB, right? And the angle itself, then, we could just do the arc cosine, right? And, of course, we're going to have to double that so we can have our sector angle. So our sector angle would be 2 arc cosine R divided by AB, the radius divided by the distance A to B. And of course, A to B is what we're looking for, right? So let's see here. Let's go ahead and see if we can plug that into the formula for the area of a sector. So our angle, right? 2 theta divided by 360 times the area of the entire circle. And we know that 2 theta is equal to 2 arc cosine R divided by AB, right? So we've got this kind of ugly expression right here. The area of sector A is 2 times arc cosine, the radius divided by AB over 360 times pi r squared. All right, so we're going to tuck that away. It's going to clean up pretty nice, you'll see. So we'll put that over here. Now, let's go ahead and call our other angle alpha again. We know that those two angles are supplementary because angle with the vertex of D and the other one with the other angle with the vertex of E, those are both 90-degree angles. They're supplementary. All of them add up to 360, so that means there's 180 degrees left over for these two. So if I just take 2 theta, subtract 180 by 2 theta, I end up with the angle I need. So remembering that 2 theta was that thing right there, 2 arc cosine radius divided by AB, I just substitute, and here's what I've got for my angle alpha. I've got 180 minus 2 times arc cosine of radius divided by AB. Now I'm going to plug that into my formula for the area of a sector. It is a little bit ugly. I'm going to make sure I distribute to get this nice and clean. When I first did this on paper, I made a silly mistake. I did not multiply this pi r squared times 180, and I ended up with something that was really cool and entirely wrong. So making sure we distribute very, very carefully. I'll show you. We've got this pi r squared. It's multiplying by 2 terms up here, 180 and the negative 2 arc cosine of r divided by AB. So I need to make sure that I have that pi r squared multiplying with both. So now I've got a nice little expression for the sector of A. So I've got sector of A, I've got sector of B. Let's go ahead and shrink our diagram away a little bit because we're going to need some room to do some computation here. All right, let's add these together. All right, so if you just add them together, it's just like that. No big deal. Let's go ahead and simplify this one right here. We're going to go ahead and multiply by pi r squared. There's only one term, so that's pretty easy to do. And if you look, we've got 2 arc cosine of the radius divided by AB times pi r squared. And over here we have minus 2 arc cosine of r divided by AB times pi r squared. So I'm going to put those over the same, make them one fraction. And I'm just going to rearrange these two things right here. That's no big deal at all, right? And then if you look, we have this and this are exactly opposites of each other. They're the same thing, but, one's a plus, one's a minus. We're going to subtract them. They make 0, so we're left with 180 pi r squared over 360. And of course, 180 is half of 360. So sector B plus sector A, pi r squared over 2. That is just so cool. I don't know about you, when I'm doing these problems and I get something that just works out like that, I get pretty happy. Yeah, so let's go back to what we have. We know that radius times AD is the area of the two triangles, the kite. And now we know that the two sectors add up to pi r squared over 2. And we know that the area that's in red would be the two triangles minus the sum of the sectors. We were told that is, of course, 8 root 3 minus 4 pi. That's the information we were given, all right? And we know that we have our expressions right here, the triangles or the kite minus the sector AB. Here's what we found. Right, so we're going to do a little substitution. We're going to do a little solving right here. We know that 8 root 3 is going to be equal to r times AD, and 4 pi is going to be equal to pi r squared over 2. So let's go ahead and set up our two equations. And yeah, let's solve the one for pi over here on the right. All right, so the pi is reduced. You could divide both sides by pi. They go away. Multiply both sides by 2. You get 8 equals r squared. Taking the square root of both sides, you get the square root of 8. Square root of 8 is, of course, 2 root 2. Man, gotta love that. Another really pretty answer. Let's take that 2 root 2 and let's plug it in. All right, we plugged it in there. Divide both sides by 2 root 2. Over here, we're going to reduce the 2 root 2 divided by 2 root 2. That's just equal to 1. And over here, on this side, 2 goes into 8 4 times. So without doing much simplification yet, this is what we have. 4 root 3 divided by square root of 2. Let's go ahead and rationalize that denominator. Right? Multiply by root 2 over 2, root 2 over root 2, and you get 4 divided by 2 times square root of 6. 2 goes into 4 twice, and 2 root 6 is the length of AD. Man, those are both pretty clean. Gotta love them. Right? AD is 2 root 6. The radius turns out to be BD, if you remember, 2 root 2. All right, so now let's take a look at our diagram. When I first did this question, I used the Pythagorean theorem, but there's actually something a little bit easier, and if you stay rooted in what it is you're trying to find, it might jump out at you. So I've got A to B is what we're looking for, and what A to B is it's the radius of circle A plus the radius of circle B. So it's both of them, and they're equal, and I know that because they're marked here. Well, I happen to know the radius of circle B. It's 2 root 2. I found that out just a moment ago. And that radius, it doesn't matter where it's measured, it would be measured the same there. And it turns out the radius of circle A is exactly the same, so I've got 2 of those radii lined up just like this. So I've got 2 root 2 plus 2 root 2. Well, that's 4 root 2. So A to B, the distance from A to B is 4 times the square root of 2. I think that's pretty cool. Let's take a look at our original questions right here. Our very first one we did together, and we found out that the area was 8 root 5 minus 5.21 pi. And we used that to help us figure out how to find out the length, knowing that the area of the red region is 8 root 3 plus 4 pi. And we found out 4 root 2 was the distance. I think that's pretty cool. Hey, could you maybe, with this kind of information, could you maybe write your own question? It would be kind of similar to these. I don't know. I hope so. I think that would be kind of a cool thing. Hey, if you like this video, do me a favor. Subscribe, like, comment. I really want to hear your comments. I'd love to hear what you're thinking. And if you're a math teacher or you like to do math just for fun, my Substack has a weekly fun math problem. I'll give you some resources so that if you want to use the problem for free in your classroom, you can. I've got all kinds of resources and a blog on teaching on my website on teachingmath.org. All kinds of good stuff there for you. And I have a pretty fancy, in my opinion, Teachers Pay Teachers account. So I'll leave links to all those. Please feel free to check them out. In the meantime, until next week, I hope you have a great day.